All right, here we are with example 6 in the Principles of Mathematical Induction packet. If you haven't tried this one on your own yet, then pause the video now and go try it before watching this. All right, example 6, we need to prove by induction that 3 to the n is greater than 1 plus 2n for all integers where n is bigger than 1. All right, so far I've been picking only a certain strategy of the 3 that I gave you originally to show you. Sometimes you can use more than one. It just doesn't matter which one you pick. It's up to you. So for this particular problem, I'm going to show you 2 different ways to do this. It's both going to be basically strategy 2, except remember last video I talked about how you can either run it forwards or backwards through. You can either replace all your n's with k plus 1s and then argue until you know that the thing you have must be true. Or you can start with what you know is already true and then do the algebra until you get k plus 1s where there used to be k's. I'm going to show you both ways. So for the first step, again, we have to prove the initial case. Notice in this particular problem, I have 2's put in here for the original n's. Why 2's? Well, it's integers, but this is just a greater than or less than sign, not also equal to. So in this case, n has to be bigger than 1, but an integer. So the first integer that is bigger than 1 is 2. Okay, I just want to point that out, so you have to read carefully, because usually it's 1 that's going to be your first case, but not always. So in this case, we're subbing in a 2 for all of the n's. 3 squared is 9, 2 times 2 is a 4, 4 plus the 1 is 5, 9 is bigger than 5, which we need it to be, check. Next, step 2 is the assumption step. So I'm going to assume that my statement is true for all of these integers k, right? Again, I'm just replacing all the n's above with k's from before. Now, step 3 is where we're going to do the algebra. In this case, for this video, I'm going to show you when I replace my k's with a k plus 1 and then argue until I know that it for sure definitely is true. I'll do a second video going the other way. So first, I'm going to start with the statement that I have up in my step 2. I'm going to start by moving everything on the right side to the left-hand side to make this all positive, because it's maybe a little easier showing that everything I have together when I add it or subtract it all, it has to be positive, than to show that one side has to definitely be bigger than the other side, because then I have to work with both at once. Whereas here I just have to make sure it's all bigger than 0, positive. So everything is over there on the left-hand side, positive. I'm going to start by replacing all of my k's with a k plus 1, and now I just have to do algebra and argue until I know for sure that this left-hand side definitely is positive, and then it will be true. So, similar to before, I can factor one of my base off of my 3 to the k plus 1 power. That's 3 times 3 to the k. Here I'll just distribute this negative 2 inside the parentheses to be negative 2k minus 2. Right, still with a minus 3 there, minus 1 gives me a minus 3. Right, I have to make sure that this here definitely must be positive. Well, here comes a little trick. My negative 2k, do you agree that I can change that to be negative 6k plus 4k? Right, negative 6 plus 4 does add up to negative 2. Right, this is a little trick because, and I do this because then my left-hand 3 parts all have a 3 in them. 3 times other stuff. This 6 I can factor 3 out. This negative 3 I can factor 3 out. Right? All of those I factor 3 out front. Then this 3 to the k minus 2k minus 1 has to be positive. Why? Well, look up at my first step in my third step. First step in the third step. Great. Yeah, my first statement up here, I knew for sure because I took this right-hand side and moved over to the left. I know for sure 3 to the k minus 2k minus 1 has to be positive. So that part there does have to be positive because I knew it from up there. 3 times a positive number does have to be positive. So that part I don't have to deal with. I only have to look at the other stuff that I have left. Well, this other stuff is just a 4k. Remember, k had to be a positive integer. So I know that 4 times an integer is positive, so that must be bigger than 0 as well. The whole left-hand side must be positive, so it is true for n equals k plus 1. So by the principle of mathematical induction, 3 to the n is greater than 1 plus 2n for all positive integers.